Welcome back to The Explainer. Today we're going to talk about something, something incredible. It's one of the biggest feats of modern engineering, but it's totally invisible. We're going to follow the water deep into the hidden world of pipes right under our feet to find out what really happens after you flush.
I mean, think about it. It's something we do every single day, right? Multiple times a day even, and we never give it a second thought. But what if I told you that one simple flush kicks off this massive, high-tech journey, a quest, really, to get clean water back from, what we leave behind?
Okay, so here's something that might blow your mind. When you look at wastewater, it's pretty much just water, like 99.9% water. The entire challenge, this whole enormous industrial process we've built, it all comes down to getting rid of this tiny, tiny fraction of pollutants. We're talking less than 1/10 of 1%. Isn't that wild? All right, you ready to dive in? Let's follow the water's path right as it hits the treatment plant and see some of this incredible engineering in action right from the get-go.
So, our first stop on this whole journey. Look, it's not the most glamorous part of the process, but it is absolutely essential. We're talking about getting the grit out. And you might be asking, what exactly is grit? Well, it's all that heavy, abrasive junk that can just wreck the whole system. Think sand, little pebbles, soil, stuff that gets washed in from the streets, from construction sites, heck, even from washing your floors. And getting this stuff out right away, it's totally non-negotiable. It's like the plant's first line of defense. It protects all the expensive pumps from getting ground down, it stops pipes from clogging up, and it keeps all that sand from settling in places it has no business being.
So how do they do it? Well, engineers have a couple of really clever tricks up their sleeves for this. There are two main designs for these grit chambers, and each one takes a fascinatingly different approach to the problem.
So the first one, the horizontal flow chamber, is really just a beautiful exercise in pure physics. The whole goal here is to control the speed of the water with just incredible precision. You've got to get it just right, slow enough for the heavy grit to drop out, but fast enough to keep all the lighter organic stuff floating along to the next stage.
So picture this in your head. The water is flowing forward at this really gentle, controlled pace. We're talking about 30 centimeters per second. But at the exact same time, that little piece of grit, even the slowest sinking one, is drifting downwards at only about 2 centimeters per second.
So you see where this is going, right? The engineers calculate the exact length the tank needs to be based on that difference in speed. It's designed so that every last one of those grit particles hits the bottom before the water flows out the other end. So simple, but absolutely brilliant.
Okay, now for the second method, the aerated chamber. This one uses a totally different trick. They pump air up one side of the tank, which creates this awesome rolling spiral flow. It basically acts like a mini centrifuge, It just flings the heavy grit out to the side, where it drops into a hopper.
And here's a really cool bonus that comes with the aerated method. That same rolling motion, it also helps separate out oils and grease. They just float right up to the surface where they can be skimmed off super easily. It's like a 2-for-1 deal on cleaning.
All right, so the heavy, abrasive grit is gone. Now it's time to deal with the next problem, all those lighter, organic solids that are still floating around in the water. And for this part, we're going to let good old gravity do the heavy lifting. This next stage is called primary settling. Basically, the water flows into these enormous tanks. They're called clarifiers, and everything just slows way down. To a crawl, really. You can think of it like a giant, perfectly engineered calm pond. It's all about giving those solid particles enough time to just gently settle to the bottom on their own. And you know what? The results are seriously impressive. A good primary clarifier can get rid of about 2/3 of all the suspended solids and more than 1/3 of the organic pollution. And it does all that just by slowing things down. No chemicals, just physics.
Now, these settling tanks usually come in two main shapes, rectangular or circular. And of course, each one has its own clever mechanical system for actually collecting all that stuff that settles to the bottom. So let's take a closer look at how they work.
So, in a rectangular tank, it's pretty straightforward. The water flows in a straight line, from one end to the other. And down at the bottom, you've got this system of really slow-moving chains and scrapers that just continuously push all the settled sludge toward a collection hopper at one end.
The circular ones, though, they work a little differently. The water comes in right at the center and then flows outward in all directions, just like when you drop a pebble in a pond and the ripples spread out. As the water spreads out, it naturally slows down, and that's what allows the solids to settle out. So you can see the key differences here, right? You've got the straight line flow with chain scrapers in the rectangular ones versus that radial center outflow with a big rotating rake arm in the circular ones. And while you might see rectangular tanks at some really huge plants, the circular design is way more common. You'll find them at most facilities.
Okay, so let's recap. We've gotten rid of the grit, and we've settled out a whole bunch of the solids. The water's looking a lot cleaner, for sure. But how clean is it really? How do engineers actually put a number on it and measure their success?
Right, because they can't just eyeball it and say, yeah, that looks good. They need hard data. And that's where two really important scientific tests come into play. Both are designed to measure the organic pollutants that are still left in the water.
The first one is called BOD. That stands for Biochemical Oxygen Demand. And it's a really clever way to measure how much food is in the water for microorganisms. Basically, it figures out how much oxygen the good bacteria would need to eat up all the biodegradable waste. So a high BOD means, you guessed it, more pollution.
Then there's the second test, COD, or Chemical Oxygen Demand. Now, this one is a much broader measurement. Instead of relying on bacteria, it uses a really strong chemical to break down all the organic stuff in the water. Not just the biodegradable things, but also the tougher, non-biodegradable pollutants.
And this is why having both tests is so crucial. Take a look. For regular domestic wastewater, the COD is usually about double the BOD. But look at the wastewater from a textile factory. The COD is more than 10 times higher. That's a huge red flag for the engineers. It tells them that this industrial waste is loaded with tough, non-biodegradable chemicals that are going to need some much more serious treatment.
So after all these initial physical steps, the water is a whole lot cleaner. This whole part of the process is called primary treatment. But, and this is a big but, the journey is not over, not by a long shot. The water is still full of dissolved pollutants that gravity just can't touch. And that brings us to the next absolutely fascinating stage, which is where biology takes over, and an army of tiny microorganisms is unleashed to do the real deep cleaning.